Okay, so now we're going to do color, and color magnitude diagrams in the infrared. So remember this movie, right? So the IR bands are always going to be on the Rayleigh-Jean side of the curve, except for possibly the shortest infrared wavelengths and the latest types. So pretty much all of those bands are on the Rayleigh-Jean slope. And since the slope is always the same, that means the ratio of fluxes is always the same, which means the color of stars that have no dust is 0. So when you move into the infrared, then it means you're looking at a different part of the SED than you were in the optical. Most stars that don't have dust have no color in the infrared because of the way magnitudes are defined. They're defined with respect to Vega, or rather what Vega would be if it didn't have an excess, and a difference in colors is a ratio of fluxes. So 0 color in the infrared, specifically the IRAC and MIPS, and if you have them, the Herschel bands at 0 color. Remember that doesn't mean that the measurement in one band is 0 magnitude. It means the difference in bands in magnitudes is 0 for stars without dust. Things that aren't just photospheres, things that aren't stars without dust, don't have 0 color. So you're going to find lots of infrared color diagrams just because of the things people do with them. But you still find color magnitude diagrams in the infrared as well. So in the near infrared, we have a lot of those in literature that we've been looking at because a lot of the work that's been done in IC 417 is working with 2-mass data. And so they had the near infrared data, and so they made a lot of plots. And I went through and tried to find a good example of a color or a color magnitude plot, but a lot of them aren't terribly clear. So I'm going to start with some plots that I made for IC 417, and then we'll look specifically at some plots from JOST 2017. So this is a color magnitude diagram with 2-mass data. So the y-axis is J-band, the x-axis is H minus K. Now remember, with the optical color magnitude diagram, the zero-age main sequence was diagonal from the upper left to the lower right. Now we're into the infrared. We're starting to get into the infrared, the near infrared. And so the main sequence is a lot more vertical. It's not yet vertical. It will be by the time we make it to IRAC bands. But in J and H minus K, it's still pretty vertical. The reddening is still going to push you down and to the right because it's going to make you fainter and redder. Now the fainter things here have lots more scatter. That's not really surprising because the fainter you go, the noisier you go, and so the error bars are larger, so you end up with more scatter. But when you get to the earlier types, it's pretty tight, right? We don't have any random weird guys that are too blue hanging out over here. We do down here because there's bigger error bars. Now, over on the right, you can see there's quite a few bright and red things, and there's quite a few fainter and red things. Those are the young stars. So this is a color diagram, J minus H on the y-axis, H minus K on the x-axis. Reddening is going to push you up and to the right because it's going to make it redder in both axes. Again, the green line is the main sequence, but because we're working now with near infrared, it's not a single line. It curves back on itself. So J minus H or H minus K are not particularly good ways of figuring out the temperature of a star because you have that degeneracy. You have more than one possible main sequence value for a given J minus H. Okay, so it's not good for telling temperature. You've got a lot of scatter in here because some of the stars are faint and we've lost the correspondence with distance. Here, you know that the faint things are the ones that are going to have large errors. Here, the faint things are muddled in with the bright things. So you just have to know that a lot of that scatter comes from the fainter objects that have larger error bars. The dot dash lines here are lines parallel to the reddening vector, and they sort of straddle the most of what the ranges of colors are for main sequence stars. So anything between those two bands is plausibly just a reddened main sequence star. But you can see we've got a lot of stars down here that are very red, right? These guys are the young stars. These guys are reddened young stars. So here are some plots from JOST et al. 2017. She's got J on the y-axis and J minus H on the x-axis. And she's got I don't remember if it's the main sequence or an isochrone. I think it might be an isochrone that she's plotted here in blue. Red circles are her YSO. So she's got two fields. She's got stock 8, and then she's got a similar field nearby. So it's still got the same amount of star density just because it's in the galactic plane. But her larger point is that, look, the black stars are like the field stars, and you see in the control field, they're all sort of clumping around the isochrone. But in stock 8, you've got the young stars that are very much redder on average than the field stars. You still get plenty of field stars, but the red points are the YSOs. Now she's got a couple of plots that are mixtures of IRAC and 2 mass colors. That's totally legitimate to do. They're all Vega magnitude, so they're on the same system, so that's totally good. In all of these cases, because all of her colors are blue or minus redder, reddening is going to point you up and push you up and to the right. She's got black again are the field stars, but now she has red and green are her young stars. So she's got 3.6 minus 4.5 versus K minus 3.6, and the field stars are mostly 0 color. Then you've got things that are increasingly red. So her red points, I don't know exactly how she's picked them, maybe even from this particular plot. The red ones are the most extreme young stars, and the green ones are the less extreme young stars. So you can see that all of these guys are really red in both axes. So now we have H minus K versus K minus 4.5, and it's the same basic structure, but it's a little bit more muddled. We've got a lot of field stars. We've got some field stars extending out that way, but you still have a clumping of the green and the red points that she's highlighted as young stars. Here is J minus H versus J minus 4.5. This is also that same color space. She's now, again, comparing the stock 8 field on the left with a control field on the right. So you can see that the field stars are sort of clumped near the main sequence with a handful of possibly reddened or otherwise weird things. Here she's got mostly field stars clumped around the main sequence, but then all of her young stars are very, very red. So again, the young stars are different than the neighbors. So here is another plot. This one is actually from one of my papers on, I guess it's from one of the work, the spin up to one of the papers for a cluster cluster called NGC 1333. On the y-axis, I have an IRAC color 3.6 minus 4.5, and the x-axis is an IRAC color 5.8 minus 8. The guys near 0 color are the stars without dust. And we've got a whole pile of things that are red in both colors. And those are the young stars there too. So here's 3.6 minus 4.5 versus 5.8 minus 8 from one of the very first papers written about Spitzer after it launched. And in preparation for launch, Laurie Allen and collaborators made a bunch of young star models to take into account the IRAC band passes and what colors you would expect. And so all of the different colored lines are different models that she has showing that young stars should be red. Now what's interesting here is that she's got the class 2 guys called out with this box, but look at her reddening vector. Her reddening vector is not up and to the right. It's up in 3.6 minus 4.5, which is good, but it's actually pointing blue in 5.8 minus 8. The reason for that is, remember that 10 micron absorption band from silicates that was in the movie that I showed you? That's what's going on, because you have that silicate absorption feature starting to bite into the fluxes you measure at 8 microns. And so this is one case in which reddening doesn't make you red in both axes. It makes you slightly bluer in 5.8 minus 8 because of that 10 micron absorption feature. But you can see that's some pretty large AV that she's got here, an AV of 30. There's some of her typical error bars too. All right, here's another version of that same plot, 3.6 minus 4.5 versus 5.8 minus 8. The photospheres are here. The reddening vectors are shown to remind you that things are going to be up, and this time slightly to the left. There's 2 different reddening models. That's why there's 2 different reddening vectors. The class 2s are here. These are the reddened class 2s, and the class 1s are out here, and the reddened class 1s are up there. And then you've got things that are in transition between class 1 and 2 here. So they have a large excess at 5.8 minus 8, but not very much of one in 3.6 minus 4.5. So there are things that have inner disk holes. So the main takeaway points from this section, remember, of course, that colors are differences in magnitudes, which are ratios of fluxes. And plots of both colors and magnitudes help you study the properties of objects you know, and then you can apply that to understand the nature of objects you don't know. The infrared points are going to be basically all on the Rayleigh-Jean side of the SED. So the IR colors are always going to be 0 for stars without dust. In other words, things that match the SED of a star without dust. Colors that are not 0 are going to tell you about things that don't look like plain stars, like stars with dust. The infrared colors and magnitudes really do a really good job of helping you find stars with circumstellar dust, but it will also help you find active galactic nuclei and asymptotic giant branch stars and other contaminants.